black holes are not cosmic vacuum cleaners. They are places where gravity becomes so extreme that space and time themselves begin to break. From far away, a black hole looks simple, a dark sphere in space. But near it, reality starts to warp in astonishing ways. The glowing ring around many black holes is called an accretion disk, superheated gas racing at incredible speeds before crossing the point of no return. Imagine drifting closer. Long before you touch the edge, the black hole begins changing how you see light, distance, and time. That dark boundary is called the event horizon. It is not a surface you can stand on, but a limit beyond which nothing escapes. Near the horizon, gravity bends light so strongly that the entire universe appears twisted around the black hole. Not all black holes behave the same. A small stellar black hole is deadly fast. A supermassive one can be strangely gentle at first. Near a smaller black hole, gravity changes sharply from your head to your feet. That difference can stretch you into a thin stream. Near a supermassive black hole, the gradient is weaker at the horizon. You might cross it without feeling anything dramatic at all. But something else changes dramatically. Time. Strong gravity slows time relative to anyone watching safely from far away. As you fall, your signals take longer to escape. Each message becomes weaker, redder, and more delayed. To a distant observer, you seem to slow down near the horizon, fading and freezing just before you cross. From your own point of view, though, nothing freezes. You continue falling inward, straight toward the unknown. Crossing the event horizon would not look like hitting a wall. There is no flash, no signpost, no dramatic border in space. Once inside, every possible future path points deeper inward. Moving away from the center becomes as impossible as moving backward in time. The universe behind you compresses into a shrinking ring of light. The rest ahead becomes a fall into darkness. One way to picture it is this. Space-time itself is flowing inward faster than light can climb back out. Tidal forces keep growing. Eventually, they overwhelm matter itself, stretching and squeezing everything that falls too deep. A spacecraft would first creak, then crack, then tear apart under the uneven pull of gravity. Inside a giant black hole, that destruction may come later. But later still means it is still coming. Physics predicts strange possibilities for rotating black holes, but deep inside, our best theories start to lose their grip. Then comes a different mystery. Stephen Hawking showed black holes may not be completely black after all. Over unimaginable spans of time, they may leak tiny amounts of energy and slowly evaporate. That creates a huge puzzle. If a black hole can disappear, what happens to everything that fell inside it? This is the information paradox, one of the deepest unsolved problems in modern physics. And these objects are not rare curiosities. Most large galaxies, including our own, hide supermassive black holes at their centers. Sometimes a star gets too close, and gravity tears it apart, feeding the black hole in a violent burst of light. We have even imaged one indirectly, capturing the glowing shadow of a black hole against infalling matter. So what really happens at the edge? It is the moment escape ends and gravity fully takes command of your future. To the outside universe, you seem to freeze. To yourself, the journey continues inward without pause. That split between viewpoints is what makes black holes feel less like objects and more like cracks in reality. At the center lies the singularity, where our current physics stops giving trustworthy answers. So the edge of a black hole is not just a place in space. It is a boundary between the known universe and the unknown. And that is why black holes remain among the most fascinating things we have ever discovered.